Hello, everyone. We're the CubeCats. I'm Ahil.
I'm Steven.
I'm Rima.
I'm Sweta.
I'm Sabrina, and welcome to our design review video.
We're a team from Whitney High School who come from a variety of backgrounds, but share a common goal of working to improve the world around us by promoting accessibility and diversity in technology.
Our mission statement, or our mission, is to effectively detect plastic in the ocean from space by developing a CubeSat. We plan to use machine learning to automate the plastic detection process. Our CubeSat will take images using the Raspberry Pi camera over a selected area of water. These images will then be sent through a machine learning algorithm to identify plastic. Now we will discuss how our CubeSat will fulfill smart requirements through each subsystem. Structure subsystem. The frame of our CubeSat will remain in a 10 by 10 by 10 centimeter cube. For verification, we would check the overall structural integrity. Power subsystem. The CubeSat will have sufficient battery to remain fully operational and perform its necessary functions for the 15-minute demo duration. For verification, we would have to run the CubeSat for 15 minutes to check whether there is still sufficient battery. For the command and data handling subsystem, the CubeSat machine learning algorithm will be able to correctly identify plastic in images 80% of the time. For verification, we will run the ML algorithm beforehand and verify its accuracy. For the communication subsystem, the CubeSat will be able to communicate with the ground station using Bluetooth. For verification, we would ping the CubeSat and wait for a response. In the imaging subsystem, the Raspberry Pi camera will be able to take high-resolution pictures of water environments. For verification, we would test the camera by taking images and ensuring that they are of high quality. For the ADCS, Attitude and Determination Control subsystem, the CubeSat will be able to correctly orient itself using pitch, yaw, and roll measurements. For verification, we would test the subsystem and make sure it determines the correct orientation using those measurements. The CubeSat will meet all subsystem requirements by May 7th, and this is verified by the demo.
Now we will walk through the CubeSat concept of operations. During the pre-launch phase, the CubeSat undergoes self-testing to ensure that all components are functioning. This would entail making sure that the camera is able to capture images, the Raspberry Pi is able to communicate with the ground station, the IMU is able to determine its orientation correctly, the battery is able to sufficiently power the mission duration, and that an image gets captured and a threshold value is calculated for each image with our plastic detection machine learning algorithm. During the launch phase, the CubeSat is launched and inserted into orbit. During the post-launch phase, the CubeSat undergoes self-testing to ensure that no components were damaged by launch. This would include making sure that all the components from the pre-launch phase are adequately tested. For example, the machine learning algorithm, the battery, the IMU, the camera, and the Raspberry Pi. If self-testing results in an error, the CubeSat will move to an error contingency in an attempt to resolve it. If error contingency fails, the CubeSat would move into a failure mode where it would try to restart the problematic subsystem. For instance, one failure mode would be camera failure, where the camera is unable to capture pictures. Then the CubeSat would attempt to restart the camera. If the machine learning program sends up errors, the program will run through a backup program, and instead the images would be directly sent to the ground station, where they could be manually sorted between plastic and not plastic. With self-testing successful, the CubeSat begins its on-orbit procedures. The CubeSat takes measurements from the IMU to orient itself correctly, and then the CubeSat would capture images of the selected water environments and identify plastic in the images with its machine learning algorithm running on the Raspberry Pi. Images with high confidence of plastic present would be sent to the ground station during communication mode. By only sending images with a high confidence of plastic, less data would need to be transmitted, meaning data space and power would be conserved.
Now we will walk through the CubeSat system level block diagram, which consists of a structure subsystem, power subsystem, command and data handling subsystem, communication subsystem, imaging subsystem, and the ADCS subsystem. The structural subsystem is the physical structure of the CubeSat. The body of the CubeSat is composed of acrylic panels connected by 4 aluminum corner rails. Interior parts are supported by the nylon standoffs. The power subsystem supplies power to the CubeSat and consists of the battery, and the battery powers the Raspberry Pi. In the command and data handling subsystem, subsystem, it coordinates with other subsystems to run the CubeSat. And it consists of the Raspberry Pi, which communicates with the ADCS, communication and imaging subsystem. The ADCS, or Attitude Determination and Control Subsystem, determines the orientation of the CubeSat using pitch, yaw, and roll measurements. The subsystem consists of the IMU, inertial measurement unit, and which contains a magnometer, gyroscope, and an accelerometer. The IMU communicates the orientation to the Raspberry Pi. The imaging subsystem captures images and consists of the Raspberry Pi camera. The camera sends the images to the Raspberry Pi. The communication subsystem consists of the ground station, which the Raspberry Pi sends the images and other information to via Bluetooth.
Now we will walk through our CubeSat CAD model. The CubeSat structure consists of acrylic panels supported by 4 aluminum side brackets. Attached to the top panel is a CubeSat battery, a T-core power bank that can supply 37.75 watt-hours of power. Attached to the bottom panel is a Raspberry Pi 4, connected to the Raspberry Pi camera and IMU. The Raspberry Pi is supplied with power from the battery through a Type-C to USB cable.
For our mass budget, we use the 10% contingency. The subsystem mass for structure is 384 grams, with the largest portion coming from the acrylic panels. The subsystem mass for other subsystems is 465 grams, with the largest portion being the battery. Since we decided not to use the solar panel as we were not able to get sufficient solar power to power our CubeSat, the energy to power our system will all come from the battery. The USB adapter board is also not included in our budget as it is not part of our CubeSat design. For our bill of materials, the total cost of components for the demo is around $210. This is broken down into $60 for structure components and $150 for other subsystem components.
For our power budget, we measured the voltage and current of each component using a multimeter, and then multiplied each component's voltage and current to calculate its peak power. We found that the Raspberry Pi, followed by the camera, consumed the maximum amount of power. We also found that the solar panel is insufficient to power the CubeSat as it only has a power gain of 0.0041 watt-hours. The estimated charging time for the solar panel would be 282 days, and it would have to supply about 13 times more power to be sufficient for our CubeSat. So we decided on instead using the 27.75 watt-hour battery pack to power the CubeSat for the duration of the tech demo and CubeSat mission.
Our software architecture consists of 3 parts: the human component, the ground station software system, and the CubeSat software system. The CubeSat software system is responsible for taking the images, identifying plastic in the images, and sending the images to the ground station. The CubeSat's IMU software first determines the orientation of the CubeSat. If the orientation is correct, the Raspberry Pi takes images of the selected areas of water for the mission. These images are then sent through a plastic detection algorithm developed through machine learning. The algorithm identifies plastic in images and boxes them. If the algorithm has high confidence that plastic is present in the image is sent to the image database on the SD card to be stored. The ground station software, in this case a Windows terminal application running a Python script, is responsible for receiving images from the CubeSat and displaying them to the human component. When the CubeSat is in communication mode, images stored in the image database are sent by Bluetooth to the Windows terminal application, where they are displayed to the human component. The human component, in this case, an oceanographer studying the presence of plastic in the ocean, views the images on the Windows terminal application. For our link budget, we made the decision to calculate our budget using the given parameters on the EDX course for a low Earth orbit satellite antenna communicating with a ground antenna, as we do not have all the data to calculate the demo channel capacity. The frequency would be 437 megahertz, the orbit 400 kilometers, and the bandwidth 1 megahertz. The ground antenna has a 12 dBi gain, 10 watt transmit power, 160 K noise temperature. The satellite antenna has a 0 dBi gain, 1 watt transmit power, and 270 K noise temperature. Using these values, we calculated the channel capacity of our CubeSat using the Shannon formula, which would directly be above the ground station at a distance of 400 kilometers. The uplink rate is 4.91 megabits per second, and the downlink rate is 4.48 megabits per second. For our data budget, we split it between housekeeping and imaging. Housekeeping data includes the satellite status updates downlinked to the ground station, which consists of the satellite's temperature, health, and remaining power. The data is estimated to not exceed 1 kilobyte and therefore is negligible in the data budget. Imaging data is the images the CubeSat sends to the ground station. Each image is 1030 kilobytes, so at an optimal downlink rate of 4.48 megabits per second, it will take 23 milliseconds to transfer one image to the ground computer. For the demo, we plan to take 10 images, which would be 10,300 kilobytes and take approximately 2.3 seconds to downlink.
Finally, we will discuss our integration and test plan, which consists of 2 parts, integration and function testing, and then environmental testing and pre-delivery. Integration and function testing consists of first, structural integration. We will test this by checking the CubeSat structural integrity. Second, power integration and testing. We will test this by checking if power is being delivered to all components and checking if the battery is at full capacity. Third, flight software and integration and testing. We will test this by checking if the Raspberry Pi is functioning and able to communicate with other components. Fourth, communications, integration, and testing. We will test this by checking if the CubeSat is able to communicate with the ground station. Fifth, attitude and determination control subsystem integration and testing. We would test this by checking if the CubeSat is able to correctly determine orientation. Sixth, imaging, integration, and testing. We would test this by checking if the CubeSat is able to take pictures. Environmental testing and pre-delivery consist of simulated testing. We will simulate a water environment by having the CubeSat move over images of the ocean and take pictures. The CubeSat will then be tested on its ability to identify plastic in the images and relay them to the ground station, in this case, a nearby laptop. We will keep track of the false positives and negatives of the machine learning algorithm to help improve the algorithm's accuracy. This testing overall ensures that the subsystems can interact and work with each other so that the CubeSat can properly carry out its mission.
Thank you for listening to our presentation. We want to thank our amazing mentors, Gary, Robert, and Shannon, who offered us invaluable advice and we're always happy to help. And thank you to the staff at BWSI and SWE who made this challenge possible.